7 earthquakes struck the most violent stretch of the Ring of Fire in 36 hours this weekend, and they did not land randomly. They formed two tight clusters, 1,000 kilometers apart, at either end of the one section of ocean floor that the sixth largest earthquake ever recorded left unbroken 13 months ago. Between those clusters sits a silent gap, a loaded section of fault on the same arc where, in 1952, a wave the height of a 6-story building erased an entire town, and the government that ruled it hid the dead from history. The rest of the planet went seismically quiet this week. This one boundary did not. Tonight we find out what those 7 earthquakes were trying to outline, and what happens on the day the silent middle finally speaks. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. 36 hours on the arc. 7 earthquakes hit the same fault system in 36 hours this weekend, and almost nobody on Earth noticed. They started on the morning of August 3rd, Universal Time, and they kept coming through the afternoon of August 4th. Magnitude 4.5, 4.7, 4.9, one after another, all of them landing on a single curved line of ocean floor in the Northwest Pacific. That line runs about 2,100 kilometers, from the coast of Russia's Kamchatka Peninsula in the north, down through the Kuril island chain, to the waters off northern Japan in the south. Geologists call it the Kuril-Kamchatka Arc, and if you wanted to nominate one stretch of the planet's surface as the most violent, this would be the leading candidate, a boundary that has produced more truly great earthquakes in the last 75 years than almost any other structure on Earth. Here is the part that matters, and I am going to give it to you up front rather than making you wait 2 hours for it. These 7 earthquakes did not scatter randomly along those 2,100 kilometers. They organized. They formed 2 distinct groups, one cluster in the north, near the southern coast of Kamchatka and the northernmost Kuril Islands, and one cluster far to the south, around the island of Shikotan, where the Kuril chain hands off to the Japan Trench. Between those 2 groups, in the central section of the arc, there was almost nothing. Silence. And that silent middle section is not just any piece of fault. It is the section that the largest earthquake of the last 15 years, the magnitude 8.8 that ruptured off Kamchatka in July of 2025, a little over 1 year ago, left behind. That earthquake tore roughly 500 kilometers of the plate boundary and then stopped. Everything south of where it stopped is still locked, still loaded, still carrying the strain it has been accumulating for decades or longer. This weekend, the earthquakes showed up at both ends of that unbroken section, not in the middle of it, at its edges, as if the fault system were tracing the outline of the one piece it has not yet dealt with. Let me walk you through the actual catalogue, because the specifics are what separate a real pattern from a scary story. On August 3rd at 10:17 in the morning Universal Time, a magnitude 4.5 struck near the east coast of Kamchatka, about 50 kilometers down. A little over an hour later, at 11:26, a magnitude 4.9 hit the northern Kurils at a depth of 76 kilometers, deep inside the descending slab of the Pacific Plate itself. At 14:39, a magnitude 4.7 struck the southern end of the chain, 49 kilometers deep, at the latitude of the island of Shikotan. At 21:42 that night came another magnitude 4.9, east of the Kurils, and this one was shallow, less than 10 kilometers deep, which puts it up near the boundary where the 2 plates actually grind against each other. Through the same window, the catalogue logged a magnitude 4.9 about 204 kilometers southeast of a town called Severo-Kurilsk, 10 kilometers deep. Another magnitude 4.9 85 kilometers south of that same town, nearly 58 kilometers down, a magnitude 4.7 61 kilometers south of Shikotan, a magnitude 4.5 85 kilometers south-southeast of Shikotan. And spilling over onto the adjacent Japan Trench, the next segment of the same plate boundary, the one that produced the 2011 Tohoku disaster, a magnitude 4.5 east of the city of Miyako on August 3rd, and a magnitude 4.6 east of Onagawa on the afternoon of August 4th. Hold on to that town name from the northern cluster, by the way. Severo-Kurilsk. The seismic catalogues use it as the reference point for the northern Kurils. Every earthquake up there gets measured by its distance from that town, 85 kilometers south of Severo-Kurilsk, 204 kilometers southeast of Severo-Kurilsk. There is a reason that name is going to matter enormously later in this video, and it is not a geological reason, it is a human one. I will just say for now that the instruments measuring this weekend's earthquakes are measuring them by their distance from a place that has already been erased once, and almost nobody outside Russia has ever heard the story, because the government of the time made sure of it. Now, you might reasonably say, these are magnitude 4s. The planet produces magnitude 4s constantly. A 4.9 releases roughly 1/30,000th of the energy of that magnitude 8.8 from last year. On any normal week, a handful of 4s on a subduction zone would not be worth 2 hours of your evening, and on a normal week you would be right. But this was not a normal week, and that is the second thing that makes this burst legible. While this one arc was producing 7 earthquakes of magnitude 4.5 or greater in a day and a half, the rest of the planet went quiet. The global count of earthquakes at magnitude 4.5 or above, measured over a rolling 7-day window, fell from 150 last week to 126 this week. That is a 16% drop. The largest earthquake anywhere on Earth during this window was a magnitude 5.2 under central Peru, a deep one, 130 kilometers down, unrelated to anything in the Pacific Northwest Rim. There were 2 magnitude 5.1s, one south of Tonga and one south of Fiji, and that was it. No magnitude 6 anywhere on the planet in days. The global seismic energy budget, if you want to think of it that way, went slack. So the picture is this: a planet that got quieter and one boundary that got busier. A burst that did not scatter, but organized into 2 groups, and a quiet zone between those groups that happens to be exactly the section of fault that the 6th largest earthquake ever recorded left unbroken 13 months ago. Any one of those facts alone is unremarkable. All 3 together are why we're here tonight. I want to be straight with you about what this video is and is not, because this channel does not do prophecy. Nobody, not me, not the United States Geological Survey, not the Russian Academy of Sciences, not the Japan Meteorological Agency, can tell you whether the section of fault between those 2 clusters will rupture next week, next decade, or 50 years from now. Roughly 19 out of every 20 clusters like this one resolve into nothing at all. The honest base rate says this is most likely the arc settling, working through the leftover stress of last year's giant, and in 3 months this weekend will be a forgotten line in a catalogue. That is the most probable outcome, and I will keep saying so throughout this video. But the reason you watch this channel is that most probable is not the same as certain, and the gap between those 2 words is where all the interesting questions live. Because the same base rate that says 19 out of 20 clusters mean nothing also says 1 out of 20 means something. Because this specific arc has a documented habit, proven on the record in the instrumental era, of failing in sequences, one segment triggering the next, sometimes with a delay of exactly the kind of interval we are now inside. And because the last time the northern end of this arc fully let go, in 1952 the result was one of the deadliest tsunamis in recorded history, and the world did not find out for decades, because the count of the dead was locked in a safe. So here is how tonight is going to work. We're going to reconstruct what actually happened in those 4.5 minutes in July of 2025, when the fault tore for 500 kilometers and the ocean rose 19 meters against the northern Kurils. We're going to find the exact place where that rupture stopped, and understand why the place a rupture stops is, to a seismologist, the most dangerous coordinate on the map. We are going to go back to a November morning in 1952, to a town of fishermen and soldiers that made one collective decision, a completely reasonable, completely human decision that killed most of them. We are going to look at what the rest of the Pacific Plate was doing this same weekend, from the Aleutians to the coast of Oregon, because this arc is one edge of a single connected mechanical system, and the other edges were murmuring too. And we are going to end with something you almost never get from coverage of earthquakes. A specific checkable list of what would have to happen next for this pattern to matter, the exact signals that would tell us the map is becoming a plan. Because that is what those 7 earthquakes drew this weekend, whether they meant to or not, a map. The question that will hang over the next 2 hours is the simplest and hardest one in all of earthquake science. Is the map just a record of where stress used to be, or an outline of where it's going? Part 2. The fastest conveyor on Earth. Every earthquake in this story is powered by the same engine, and the engine has been running without a pause for tens of millions of years. Off the eastern coast of Kamchatka and the Kurils, the floor of the Pacific Ocean, a slab of cold, dense rock roughly 100 kilometers thick, is sliding down beneath the edge of the continent and sinking into the Earth's mantle. Geologists call the process subduction, and the line where the ocean floor bends downward is marked by the Kuril-Kamchatka Trench, a gash in the seabed that plunges to more than 10,000 meters, deep enough to swallow Mount Everest with more than a kilometer of water to spare. What makes this particular subduction zone stand out among the dozens that ring the Pacific is the speed. The Pacific plate is converging on this boundary at roughly 75 to 80 millimeters every year. That sounds like nothing. It is about the pace your fingernails grow. But fault systems do not care about human timescales. They care about accumulation. 80 millimeters a year means the boundary stores up a full meter of unspent motion every 12 to 13 years wherever the two plates are stuck together. Run that clock for a century, and you have 8 meters of built-up slip waiting to be paid out. Run it for 3 centuries and you have 25, and the boundary does not pay its debts gradually. Where the interface is locked, where friction pins the two plates together, the debt gets paid all at once, in seconds to minutes, in the events we call great earthquakes. The receipts are all over the instrumental record. Since seismometers became good enough to measure such things, this single arc has produced at least 3 earthquakes of magnitude 8.5 or greater, 1952 off Kamchatka, 1963 off the island of Urup in the central Kurils, and July of 2025, plus a magnitude 8.3 in 2006 that we will come back to later in the video because it has a twin, and the story of those twins is one of the strongest pieces of evidence for the pattern we are chasing tonight. Almost no other single subduction zone on the planet can match that count in that span. The southern coast of Alaska can argue, Chile can argue, the list of contenders ends about there. The engine does not only make earthquakes. Ride the arc from south to north, and you pass one of the densest concentrations of active volcanoes on Earth, because the sinking Pacific slab sweats water as it descends, and that water lowers the melting point of the rock above it, and the melt rises. Kamchatka alone holds dozens of active volcanoes, including Severo-Kurilsk, a mountain we covered in our video from July 22nd, when its unstable lava dome was pushing out ash clouds that forced aviation warnings across the North Pacific. If you watch that video, tonight is the other half of the same machine. The volcanoes are the engine's exhaust. The earthquakes are its drivetrain. Same slab, same descent, same energy, expressed 2 different ways. And this weekend, the drivetrain is the part that started making noise. It is worth pausing on how empty this place is, because the emptiness shapes everything about how its disasters unfold. The Kuril chain is a line of volcanic islands stretching about 1,200 kilometers, and the total population across all of them is a few tens of thousands of people, concentrated in a handful of towns. Southern Kamchatka adds the city of Petropavlovsk-Kamchatsky, home to roughly 180,000. Compare that to the Japan Trench immediately to the south, where the same style of boundary runs along a coastline holding tens of millions. The remoteness means a great earthquake here can rupture 500 kilometers of fault, raise the ocean 19 meters, and kill almost no one, which is precisely what happened last year, and which is also precisely why last year's event received a fraction of the world's attention that it deserved. The arc's very emptiness works like a silencer. The most violent stretch of the Ring of Fire is also one of the least watched, and things that happen unwatched have a way of being underestimated. There is one more property of this boundary you need before we get to last July, and it is the one that turns geology into suspense. Subduction zones do not rupture their whole length at once. They break in segments, patches of the interface, tens to hundreds of kilometers long, that fail independently. Which segment fails, and when, depends on where the interface is locked and how much strain each patch has accumulated since it last broke. A great earthquake relieves the strain on its own segment, but here is the catch, and it is the catch on which this entire video turns. It does not relieve the strain on the segments next door. It adds to it. When 500 kilometers of boundary suddenly lurch several meters, the unbroken sections at either end of the rupture get wrenched, loaded with additional stress, on top of whatever they were already carrying. Seismologists can calculate this transferred stress, and the calculation points in a consistent direction. After a great earthquake, the most dangerous real estate on the boundary is the segment immediately beyond where the rupture stopped. The 1963 event is worth a moment here, because it is the forgotten middle child of this arc's great earthquake family, and it proves the segmentation principle in one clean example. On October 13th of that year, a magnitude 8.5 ruptured the boundary off Europe in the central Kurils, a different segment than the one that had failed in 1952, 11 years earlier and several hundred kilometres to the north. Two segments of one arc, two great earthquakes, 11 years apart. The boundary did not fail as a whole, it failed in instalments, and each instalment changed the ledger for the segments that had not yet paid. You should also know that this boundary produces three distinct species of earthquake, because telling them apart is going to matter when we read this weekend's catalogue. The first species is the interface event, the big one, the megathrust, where the top of the sinking Pacific slab slips against the overriding plate along the shallow, locked contact patch. Those are the tsunami makers, and they live at depths from roughly 10 to 50 kilometres. The second species is the intraslab event, a rupture inside the descending slab itself as the cold plate bends, cracks and adjusts on its way down into the mantle. Those can happen at any depth from 50 kilometres to hundreds, and because they are deeper and do not displace the seafloor, they rarely make dangerous waves. The third species is the outer rise event, out beyond the trench, where the ocean floor flexes upward before its plunge, and the bending stretches the plate's upper surface until it snaps in extension. Each species tells you something different about the state of the machine. Interface events speak to the locked zone directly. Intraslab and outer rise events speak to the stresses being routed around and through it. A healthy, quietly creeping boundary produces a background hum of all three. A boundary that has just hosted a magnitude 8.8 produces something else, a redistribution, as every part of the system renegotiates its load. The question for any cluster on this arc, including this weekend's, is which species it belongs to and what that species is telling us about the part of the fault we cannot see. Keep all of that in mind as we go back 13 months to the moment the biggest earthquake in a generation picked its endpoint. Because everything about this weekend's little burst of magnitude 4s, the reason two clusters of modest earthquakes on a remote arc are worth your evening, comes down to where that endpoint landed and what is still sitting on the other side of it. Part 3, 4.5 minutes. On the morning of July 30th, 2025, local time, it was still July 29th in the Americas, the locked interface off the coast of Kamchatka finished a countdown that had been running since Joseph Stalin ruled the Soviet Union. Somewhere beneath the seafloor southeast of Petropavlovsk Kamchatsky, a patch of the boundary that had been pinned for decades reached the limit of what friction could hold and it slipped. In the first second, the slip was a patch of fault a few kilometres across. It did not stay that way. The rupture spread outward across the interface like a tear ripping through fabric, and the instruments of the entire planet watched it go. Seismic waves take minutes to cross the Earth, and by reading their arrival at hundreds of stations, researchers can run the process backward and watch the tear propagate, a technique called back projection. What it showed was a rupture that made a choice. Instead of spreading north up the Kamchatka coast, the tear ran predominantly southwest, down the arc toward the Kuril Islands, and it kept running. 100 kilometres, 200, 300. The published estimates of the final rupture length vary by method, from about 390 kilometres on the conservative end to as much as 600, with the back projection work resolving roughly 500 kilometres of propagation to the southwest, a figure corroborated by an entirely independent line of evidence: sound waves in the ocean itself, recorded on hydroacoustic networks, which heard the rupture travel. The fault did not just tear far, it tore hard. Across a contact patch 140 to 200 kilometres wide, the two sides of the boundary slid past each other by more than 10 metres in multiple places, and in the worst patches the slip reached 30 to 40 metres. Try to picture that. Two masses of rock, each the size of a mountain range, displacing by the length of a 10-storey building is tall, sideways and downward past each other in under 5 minutes. The total duration of the rupture, depending on which study you read, was somewhere between 190 and 270 seconds. For at least 3 full minutes, and possibly closer to 4.5, the tear was actively running, radiating energy the whole way. It is worth slowing down on how researchers actually watch this happen, because the method is one of the quiet triumphs of modern seismology, and it is the reason we can talk about the rupture's endpoint with any confidence at all. A seismometer in, say, Montana does not record an earthquake as one clean pulse. It records a long, complicated wave train, because the rupture is not a point. It is a moving source, a tear front sweeping across hundreds of kilometers of fault, radiating energy from every new patch it breaks. Back projection treats a continent's worth of seismometers as a single giant listening array. By carefully accounting for the travel time from every possible patch of the fault to every station, researchers can ask, at second 30, where was the energy coming from? At second 60? At second 90? Stack the answers and you get something close to a film of the rupture front moving. For this earthquake, the film showed the front leaving the epicentral region and driving southwest down the arc at kilometers per second, frame after frame, for hundreds of kilometers. And then a second completely independent instrument network said the same thing. Underwater microphones, hydroacoustic stations, originally built in part to listen for nuclear tests, picked up the rupture as sound travelling through the ocean itself in a wave type researchers call T-waves. The T-wave record indicated the same story, a source that moved south, about 500 kilometers worth. When two unrelated physical channels, solid earth shaking and ocean-borne sound, agree on the geometry of an event, you can take the geometry seriously. When the seismologist integrated it all, the length, the width, the slip, the rigidity of the rock, the number that came out was a moment magnitude of 8.8. I want to put that number in its proper place, because magnitude scales are logarithmic and human intuition is not. Each full step of magnitude is roughly a 32-fold jump in energy. A magnitude 8.8 is not 10% bigger than an 8.0. It is more than 15 times bigger. 8.8 is tied for the sixth largest earthquake ever recorded by modern instruments. In the entire catalogue of the instrumental era, every earthquake measured since seismometers became capable of measuring them, well over a century of records across the whole planet, only a handful of events have ever exceeded it. The magnitude 9.5 in Chile in 1960, the largest ever measured, the magnitude 9.2 in Alaska in 1964, the magnitude 9.1 off Sumatra in 2004, the magnitude 9.1 off Japan in 2011, and a magnitude 9.0 in 1952, produced by this very arc on the section immediately north of the Kurils. That is the shelf this event sits on, and notice that the shelf already holds one earlier earthquake from the same boundary. This arc is a repeat member of the most exclusive club in seismology. A magnitude 8.8 releases roughly 700 times the energy of the magnitude 7.1 that shattered buildings in Kumamoto, Japan, in late July, the earthquake we covered in our video from July 28th. 700 Kumamotos spent in 4.5 minutes on a fault most people watching this video had never heard of. And here is what should genuinely surprise you. Almost nobody died. We will spend a full part of this video on the wave it made, and the wave was enormous, but the human toll of one of the 6 largest earthquakes ever measured was minimal. Part of that was luck of geography, the emptiness we talked about. Part of it was rupture geometry. And part of it, a part that matters deeply to where this video ends up, was that the warning systems worked. Alerts went out across the entire Pacific within minutes. Coastlines from Japan to Hawaii to the Americas knew what was coming before it arrived. Hold that thought, because later tonight we are going to meet the mirror image of that outcome. An earthquake of almost exactly the same size, on almost exactly the same stretch of boundary, where the warning consisted of the ground shaking and nothing else, and where the government's contribution afterward was to hide the bodies from the historical record. The earthquake also did what every great earthquake does. It started a sequence. The United States Geological Survey published a formal aftershock forecast within days, laying out the expected decay. A population of smaller earthquakes, densest immediately after the main shock, thinning month by month according to a decay law seismologists have known for over a century. The sequence performed roughly as forecast. Within a week the region had produced aftershocks by the dozen. In early August of 2025, a magnitude 6.8 struck in the Kuril Islands region, a substantial earthquake in its own right, the kind that would lead the news if it happened under a city, absorbed here as a routine entry in a decaying sequence, and the sequence has kept decaying ever since, all through the autumn, the winter, the spring, into this summer. That decay curve matters for tonight, because 13 months out the background rate along the rupture zone should be low and still falling. When a burst of activity shows up now, organised, spatially coherent, at the edges of the rupture rather than inside it, The first question a careful observer asks is whether it fits the tail of the old sequence, or whether it is something with its own geometry. Hold that question. It is the hinge of this entire video, and we will come back to it with the actual map in front of us. But before we get to 1952, we have to deal with the question that turns last year's earthquake from a closed story into an open one. A 500-kilometer tear is astonishing. The arc, though, is over 2,000 kilometers long. The rupture that started southeast of Petropavlovsk ran down the boundary through the latitude of the northern Kurils, and then, somewhere in the neighbourhood of the central chain, it stopped. Rupture fronts always stop somewhere. The energy runs out, or the tear hits a patch of fault that is not ready to fail, a strong point, a barrier. Every great earthquake has an endpoint, and seismologists study the endpoints more intently than the epicenters. Because an epicenter tells you where the story began, an endpoint tells you where the next story is most likely to begin. The 2025 rupture's southern endpoint left everything beyond it. The central and southern Kurils, hundreds of kilometers of locked loaded interface, accumulating 8 centimeters of slip deficit a year for as long as anyone has been measuring, untouched, unrelieved, and by the physics we walked through in the last part, actively burdened with extra stress transferred from the 500 kilometers that did break. That unbroken stretch has a name now, at least on this channel. It is the gap. And on the 3rd and 4th of August 2026, 13 months after the gap was created, earthquakes began to appear in the catalogue at both of its ends, while the centre stayed silent. To understand whether that silence is comfort or warning, you need to know what the ocean did the last time this boundary moved. That is where we go next. Part 4. The wave that followed. The seafloor southeast of Kamchatka moved, and the ocean above it had no choice but to move with it. That is all a tsunami is at the moment of its birth. Not a wave in any familiar sense, but a displacement. When 30 to 40 meters of slip occur on a fault that dips at a shallow angle beneath the seabed, the overriding plate lurches seaward and upward, and it lifts the entire column of water sitting on top of it. Not the surface. The column, 4, 5, 6 kilometers of ocean, hoisted in minutes across a region hundreds of kilometers long. The sea surface bulges, gravity pulls the bulge back down, and the energy has nowhere to go but outward, in every direction at once, at the speed of a jet airliner in deep water. Out in deep water, a tsunami is nearly invisible, and that invisibility is central to why these waves kill. The disturbance crossing the open Pacific is not a towering wall. It is a broad swell, often less than a meter high, but with a wavelength of hundreds of kilometers, moving at a speed set by the depth of the water beneath it. Over a 4-kilometer deep ocean that works out to roughly 700 kilometers per hour. A ship at sea rides over it without noticing. The energy is there, but it is spread through the whole water column and stretched across an enormous wavelength. The transformation happens at the coast. As the wave runs into shallowing water, it slows dramatically, and the energy that was distributed across hundreds of kilometers of fast-moving water piles up into a shorter, taller, slower mass. The swell nobody could see becomes a rising ocean that does not stop rising. It does not curl and crash like a surf wave. It arrives as a flood with momentum, a tide compressed into minutes, and then it drains back out with nearly equal violence, carrying its cargo with it. That draining is often the deadlier phase, and it is going to matter enormously when we reach the events of 1952. Within minutes of the rupture on that July morning, the ocean began delivering the bill to the nearest coastlines, southeastern Kamchatka and the northern Kuril Islands, the shores directly above and beside the rupture. The survey teams that later walked those coastlines, whose findings were published in the journal Pure and Applied Geophysics, measured what the water had done by the marks it left. Stranded debris, stripped vegetation, salt-killed grass, sediment sheets. Along at least 550 kilometers of coast nearest the rupture, the run-up, the maximum height the water reached above normal sea level as it drove inland, was at minimum 2 to 3 meters. Over most of that stretch it was typically 5 to 10 meters. That is already a destroying wave. 5 meters of moving ocean removes wooden buildings from their foundations, but over one particular 100-kilometer stretch of the Kamchatka coast, the run-ups reached 10 to 16 meters, and in the northern Kuril Islands, the survey found watermarks at 19 meters, the height of a 6-story building. Stand at the base of a 6-story building, Look up at the roof line and imagine the ocean arriving at that height, moving at highway speed, carrying everything it has already picked up. A note on what those survey numbers actually mean, because run-up is a technical term and the distinction it carries is worth 30 seconds. Run-up is the elevation above normal sea level that the water ultimately reached, measured by climbing the terrain until you find the highest line of tsunami evidence. It is not the height of the wave offshore, and different stretches of coast convert the same offshore wave into wildly different run-ups. Bays and inlets funnel and amplify, headlands split and shed. The shape of the seafloor approaching the shore focuses wave energy, the way a lens focuses light. That is how 100 kilometers of Kamchatka coast took 10 to 16 meters, while adjacent stretches took 5, and how pockets of the northern Kurils reached 19. For scale, the 2011 Japan tsunami, the one the world watched live, produced run-ups approaching 40 meters at its most extreme focused points, from a magnitude 9.1. 2025's 19 meters, from an 8.8 against mostly empty islands, belongs to the same weight class of ocean. The wave was world historical. The audience was absent. That mismatch is the entire reason this event never lodged in public memory the way it should have, and the reason this channel keeps returning to this arc while the wider world does not. 19 meters, in the northern Kurils. If you have been paying attention to the geography, a cold recognition should be arriving about now. The northern Kurils are the home waters of that town the catalogues keep referencing, Severo-Kurilsk, the reference point for this weekend's northern cluster of earthquakes. In 2025, the 19-meter run-up found mostly empty shoreline because the settlements of the northern Kurils are few, small and, for a reason we have not yet told you, sighted more carefully than they once were. The wave was, in the strictest sense, a near miss, a world-class tsunami delivered to one of the least populated coastlines on the Pacific Rim. The last time this boundary sent water like that at those same islands, the shoreline was not empty, and the sighting was not careful. That story is 2 parts away, and I promise it will reframe everything you have heard so far. Farther from the source, the wave spread across the entire Pacific Basin, and the entire basin had been warned. This is the part of the 2025 event that deserves more credit than it ever received. Within minutes of the rupture, the seismic networks had a location and a preliminary magnitude. Within roughly a quarter of an hour, tsunami warning centers were issuing guidance across the ocean. Deep water pressure sensors, the dart buoy network, instruments sitting on the abyssal seafloor that feel the pressure change as a tsunami passes over them, caught the wave in transit and confirmed its size, letting forecasters refine their coastal predictions in real time. Japan evacuated stretches of its Pacific coast. Hawaii activated its warning system and moved people off the beaches. Alerts ran down the coasts of North and South America. When the wave arrived, smaller with distance but still measurable everywhere from Alaska to Chile, the coastlines it reached were, overwhelmingly, ready for it. The 6th largest earthquake ever recorded put a tsunami into every corner of the largest ocean on Earth, and the global death toll was minimal. As a demonstration of what open data, fast networks, and international cooperation can do, it is close to the best case the modern warning system has ever delivered. The dart buoys deserve one more beat, because they are the least appreciated instruments in this whole system, and they will appear again in our watch criteria at the end of tonight. Each station is a pressure recorder sitting on the abyssal sea floor, sensitive enough to detect the weight of a centimetre scale change in the height of the entire water column above it, through 4 or 5 kilometres of ocean. When a tsunami passes overhead, the recorder feels the pressure rise and fall on the wave's long period, distinguishes it from wind waves and tides by that period, and relays the measurement by acoustic link to a surface buoy, and from there by satellite to the warning centres, within minutes. This is the difference between forecasting a tsunami from the earthquake alone, which tells you roughly how much water might have moved, and measuring the actual wave in transit, which tells you what is truly coming. In 2025, the network did exactly that, and coastal predictions tightened in real time as the wave crossed each sensor line. Remember the principle. The modern system does not ask you to trust a model. It publishes the measurements, from open instruments, as they happen, to everyone at once. I keep underlining that success for a reason beyond fairness. Tonight's story runs on a comparison, and the comparison only lands if you hold both halves of it. Here is the first half. In 2025 on this arc, the planet's monitoring system saw a great earthquake the moment it happened, told everyone, and people lived. Keep it in hand. The second half is coming, and it is the dark twin of everything in this part. Same boundary, same style of wave, nearly the same magnitude, and a warning system that consisted of nothing at all. But first, we owe the central question of this video its due. The wave of 2025 was made by the 500 kilometers of fault that ruptured. The clusters of this weekend are gathered around the section that did not. So the question that actually matters, the one the rest of this video is built to answer as honestly as the evidence allows, is what happens at the moment the gap stops being a gap. To reason about that, you need to understand why ruptures stop where they stop, and what a stopped rupture does to its neighbours. That is part 5, and it is where the physics of this story stops being descriptive and starts being predictive. Part 5, where the rupture stopped. Every rupture front dies somewhere, and seismologists have spent decades trying to understand what kills them. A tear that has been propagating at 2 or 3 kilometers per second, feeding on the strain energy stored in the locked interface, does not stop for no reason. Broadly, 2 things can stop it. It can run into a section of fault that has already spent its energy, a patch that ruptured recently, where there is simply not enough accumulated strain to keep the front fed. Or it can run into a barrier, a patch that is strong or oriented unfavourably or mechanically different, a subducted seamount, a change in the sediment on the downgoing plate, a bend in the trench, a section where the plates creep quietly instead of locking. The front arrives, the patch refuses to fail at that moment, and the tear starves. Here is the crucial point, and I want to state it with care. A barrier that stops a rupture is not a wall that protects the fault beyond it. It is a bookmark. The strain on the far side of the barrier is still there. Worse, the rupture that just died against the barrier has added to it. When 500 kilometers of interface slip by tens of meters, the block of crust beyond the rupture's end gets dragged, twisted and squeezed. Seismologists model this with a quantity called Coulomb stress, a bookkeeping of how a given slip event changes the push and the clamp on every nearby fault surface. The details are gloriously complicated, but the headline result from 3 decades of this modelling is consistent. Great ruptures load the along-strike segments beyond their endpoints. The place a rupture stops becomes, statistically, the most likely place the next one starts. Not certainly, not on any known clock, but the dice are reweighted. Let me make the stress bookkeeping concrete with a mechanism you can hold, because Coulomb stress sounds abstract and the reality is anything but. Whether a fault patch fails depends on a competition between 2 forces, the shear stress trying to slide the 2 sides past each other, and the clamping stress pressing them together multiplied by friction, holding them locked. Think of a heavy crate on a loading ramp. Gravity along the ramp is trying to slide it. The crate's weight into the ramp is holding it, and it moves the instant the first force wins. A great earthquake nearby changes both numbers at once for every fault in the region. Depending on the geometry, it can add to the sliding force, or ease the clamp, or both. And a patch that was decades from failure on its own schedule gets moved years or decades closer in a single afternoon. The changes are small in absolute terms, a fraction of the stress the fault will ultimately release. But faults that are already near failure do not need a large push. They need a last one. That is why the aftershock maps of great earthquakes light up not only the rupture itself but the surrounding fault network, and why the segment beyond a rupture endpoint, which receives the largest along-strike load, earns its place at the top of the watch list. The Pacific has staged this play before, and recently enough that the performances were fully instrumented. On December 26, 2004, the Sumatra-Andaman earthquake, magnitude 9.1, ruptured well over 1,000 kilometers of the Sunda boundary and stopped at its southern end near the island of Simulu. 3 months later, almost to the day, the segment immediately south of that endpoint failed. The Nias earthquake of March 2005, magnitude 8.6, one of the largest earthquakes of the century in its own right, nucleating essentially where its predecessor had quit. 3 months. The stress transfer calculations published afterwards showed exactly what you would expect. The 2004 rupture had loaded the Nias segment toward failure, and this arc, the one we are watching tonight, has its own documented sequel, which is why no one who studies the Kurils treats segment triggering as a hypothetical. On November 15, 2006, a magnitude 8.3 ruptured the interface in the central Kurils, a segment that had been suspiciously quiet for as long as records existed, a recognized seismic gap that finally paid out, sending a tsunami across the Pacific. 59 days later, on January 13th, 2007, a magnitude 8.1 struck almost the same coordinates, but not on the interface. It was an outer rise event, the third species from our earlier taxonomy, the oceanic plate seaward of the trench, snapping an extension. The 2006 rupture had unclamped the outer rise, and the outer rise responded with one of the largest extensional earthquakes ever recorded. Two great earthquakes, 59 days apart, the second a direct mechanical consequence of the first, on this arc. Within the professional lifetime of every seismologist working today, the delay between a great earthquake and its sequel, when a sequel comes, has no fixed length, and the historical spread is exactly why nobody serious will give you a date. 59 days separated the 2006 and 2007 Kuril twins. 3 months separated Sumatra from Nias. On the Nankai boundary off southern Japan, a different arc, same physics, the 1944 rupture of the eastern segments was followed by the 1946 rupture of the western segments. A 2-year gap between halves of what was, mechanically, one strain system paying out in installments. And sometimes the delay is measured in decades, or the sequel simply does not come in any time frame that matters to the people watching. The honest statement is that stress transfer changes probabilities, not schedules. What it emphatically does not do is subside. Transferred stress does not decay away like an aftershock sequence. It sits in the rock, permanent, waiting to be either released by rupture or slowly modified by the deep, ductile creep of decades. The load the 2025 earthquake placed on its neighbours in 4.5 minutes is still there tonight, undiminished, 13 months later. That is worth restating plainly. The gap is not recovering. Gaps do not recover. They wait. So when the 2025 rupture died somewhere near the central Kurils, every specialist in the field understood the implication without needing it spelled out. The segments beyond the endpoint, the central and southern Kurils, down toward the junction with the Japan Trench, moved up the watch list. Not because anyone predicted an earthquake there, but because the arithmetic of stored strain plus transferred stress says that is where the system's attention now lives. People who monitor the daily catalogues have described the pattern in plainer language. Subduction zones sometimes unzip. One segment goes, and then, on a delay of days to months to years, the next one down the line goes, the way it has been observed on the boundary off Peru and Chile, where a large event at one latitude is followed, some odd months later, by a larger one farther along the line. Slow unzipping is a metaphor, not a mechanism, and I want to keep the two separated. But the mechanism underneath the metaphor, stress transfer into loaded neighbours, is as solid as anything in earthquake science. Now add the last ingredient. Time. The central and southern Kuril segments have their own strain clocks, running at that 75 to 80 millimeters per year we established earlier, and those clocks have been running a long while. The southern Kurils hosted great earthquakes in the 20th century. The region off Hokkaido and the southernmost islands has broken at magnitude 8 class more than once in the instrumental record. But substantial sections of the chain have not produced a full-size interface rupture in many decades. Every year that passes adds another 8 centimeters to the deficit. The 2025 earthquake then added its transferred stress on top, concentrated at the segments adjoining its endpoint. That is what we mean, precisely, when we call the gap loaded, a section of one of the fastest converging boundaries on Earth, carrying decades of unspent slip, freshly burdened by the 6th largest earthquake ever measured, bracketed by a boundary that has already proven, twice in 2005 terms and in 2007 terms, that its segments talk to each other. Which brings us back at last to the 3rd and 4th of August 2026 and to the actual shape of what happened this weekend. Because if you were designing a signal to test whether the gap is being worked on, if you asked what the minimum detectable symptom of a loading segment would look like, it would look uncomfortably like what the catalogue just produced. The question is whether that resemblance is meaningful or coincidental, and there is exactly one honest way to find out. Put every event on the map one by one and see what the map actually says. That is Part 6. Part 6. Reading the map. 10 entries. That is the whole data set for this weekend. 7 earthquakes of magnitude 4.5 or greater on the Kuril-Kamchatka arc proper, 2 on the adjacent Japan Trench, and 1 smaller, deeper event reported below the catalogue threshold. 10 entries against 2,100 kilometres of boundary. It is not much data, and every conclusion in this part has to be held with a corresponding looseness. But even 10 entries have a geometry, and the geometry is the story. Start in the north. The magnitude 4.5 near the east coast of Kamchatka, 50 kilometres deep, sits at the top of the arc, within the broad footprint of last year's rupture zone, plausibly a late ordinary member of the decaying aftershock family. The magnitude 4.9 at 76 kilometres depth in the northern Kurils is deep intraslab, the descending plate cracking internally as it renegotiates its bends and loads. The magnitude 4.9 that struck 85 kilometres south of Severo-Kurilsk at 58 kilometres depth is intraslab as well, but its position matters. It sits at the latitude band where the 2025 rupture was approaching its end. And then there are the 2 shallow ones. The magnitude 4.9 east of the Kurils at under 10 kilometres, and the magnitude 4.9 204 kilometres southeast of Severo-Kurilsk, listed at 10 kilometres, shallow near the trench, in the neighbourhood where the rupture terminus meets the unbroken chain. Depth that's shallow, that far seaward, put an event in the vicinity of the interface itself or the outer rise. The 2 species that speak most directly to the state of the locked zone and its clamp. Now jump 1,000 kilometres south. The magnitude 4.7 at the latitude of Shikotan, 49 kilometres down. The magnitude 4.7 61 kilometres south of Shikotan at 35 kilometres. The magnitude 4.5 85 kilometres south-southeast of Shikotan, also 35 kilometres. 3 moderate events in a day and a half stacked at the southern end of the Kuril chain, the far side of the gap, where the arc hands off to the Japan Trench. And immediately beyond the handoff, the trench picked up the theme, a magnitude 4.5 east of Miyako and a magnitude 4.6 east of Onagawa, both around 35 to 40 kilometres deep, both on the boundary segment that ruptured catastrophically in 2011. There was also, according to the monitoring feeds that watch this region around the clock, a deep magnitude 4.4 at roughly 105 kilometres down near the northern end of the Japan area subduction system, below the threshold of the main catalogues and unverified individually, but consistent with the same picture. The deep slab adjusting while the shallow boundary chatters. Put it all on one map and the shape is unmistakable. A northern group hugging the southern end of the 2025 rupture. A southern group gathered at the far end of the unruptured chain and bleeding into the Japan Trench. And between them, across the central Kurils, the very section that the rupture left loaded. The section with the 2006 and 2007 Great Earthquake pedigree. Nothing above the detection floor. The burst did not fill the gap, it framed it. There is a timing observation to log here as well, though it needs to be handled with tweezers. This burst arrived almost exactly 1 year after the main shock, July 29th, 2025 to August 3rd, 2026. Anniversaries do strange things to pattern-hungry minds, and I want to be explicit that the rock does not know what month it is. There is no annual cycle in subduction mechanics, no candle on this cake. If the timing means anything at all, it is only through the boring channel. 13 months is enough time for an aftershock sequence to decay to a whisper, which lowers the background noise and makes any new, spatially organized signal easier to see. The anniversary does not make the burst more dangerous. It makes it more legible. The distinction matters because half the bad earthquake analysis on the internet is built on calendar numerology, and this channel does not do calendar numerology. What we do is geometry, and the geometry needs one more test before it earns your concern. That test is the one seismologists would actually run. Does this weekend fit the old sequence, or does it have its own shape? An aftershock population 13 months out should be sparse, should cling to the rupture zone itself, and should be thinning month over month on a smooth decay curve. Some of the northern events fit that description without strain. The Kamchatka coast 4.5 in particular sits comfortably inside the old footprint, but a decaying sequence should not suddenly produce simultaneous activity 1,000 kilometres south of the rupture, at the far end of the unbroken chain, in the same 36-hour window, and it should not do so while the global rate is falling, which removes the easy explanation that the whole planet was simply having a busy week. The southern cluster is the piece that does not fold neatly into the aftershock story. Either it is unrelated background coincidentally synchronized with the north, or the ark's two loaded ends are being worked on at the same time by the same redistributed stress field. 10 events cannot decide between those readings, but they can tell you which measurement will. I need to spend a full paragraph now arguing against my own map, because that is the discipline that separates analysis from storytelling. First, the Kuril ark's background seismicity is not uniform, and it never has been. The regions near southern Kamchatka and near the southern Kurils are persistently productive. The central chain is habitually quieter even in normal times, partly for real mechanical reasons and partly because the sparse regional network detects less there. Two clusters with a quiet middle is to some degree what this ark's ordinary background looks like. The weekend may simply be the background, briefly turned up. Second, with 10 events, apparent structure comes cheap. Randomness clumps. The human eye finds outlines in scattered points, because finding outlines is what human eyes evolved to do. Third, the discriminating measurement is not position but mechanism, and as of tonight we do not have it. Reviewed moment tensors, the analysis that tells you whether each event was interface thrust, intraslab compression, or outer rise extension, had not been published for these magnitude 4s as of the data cutoff. If the shallow northern pair resolve as interface thrust events at the rupture's edge, the loaded boundary reading strengthens materially. If the whole burst resolves as intraslab bending, the story softens into ordinary post-giant adjustment. That single distinction, checkable within days, is worth more than everything else in this part combined. Since moment tensors are going to carry that much weight, take 30 seconds on what one is, so the term does not float. When an earthquake occurs, the pattern of first motions radiating outward, which stations get pushed and which get pulled, in which directions at which strengths, encodes the orientation of the fault plane and the direction of slip. Analysts invert the recorded waveforms to recover that pattern and publish it as a mechanism, often drawn as the familiar black and white beach ball diagram. For our purposes, the readout is simple. An interface event at the Kuril boundary should show low-angle thrust, one side riding up and over the other on a gently dipping plane, the signature of the megathrust itself. An intraslab event typically shows steeper compression or extension inside the descending plate. An outer rise event shows extension near the trench. When the reviewed mechanisms for this weekend's shallow northern pair are published, and for anything new that follows them, that beach ball pattern is the single glance that tells you whether the locked boundary itself moved or just the machinery around it. File that away. It is watch criterion number 2 at the end of tonight. But after all 3 caveats are paid in full, one fact remains standing, and it is the fact the caveats cannot reach. The quiet centre of this weekend's map and the loaded segment of last year's rupture are the same piece of fault. The frame the earthquakes drew around the gap may be coincidence. The gap itself is not. It is a measured physical object, hundreds of kilometres of locked interface, decades of stored slip, freshly stressed at both ends, and it will fail someday, whether or not this weekend had anything to do with it, which raises the question this channel exists to ask. When it does, what exactly happens? History has already answered that question once, on this arc, in precise and terrible detail. The answer was recorded, sealed, and hidden for a generation. It is time to open it. Part 7. The Town That Went Back. At 4:58 in the morning on November the 5th, 1952, the ground under the town of Severo-Kurilsk began to shake, and it did not stop for a very long time. The town sat on Paramushir, the second island from the northern end of the Kuril chain, facing the Pacific across a modest strait, a settlement of several thousand people built low, near the water, around its harbour and its fish processing plant. The Soviet Union had taken the Kurils from Japan at the end of the Second World War only 7 years earlier, and Severo-Kurilsk was the administrative heart of the new northern district. Fishermen and cannery workers and their families, alongside a substantial military garrison, living in wooden buildings on flat ground beside the sea. Almost none of them had been on these islands long enough to inherit the one piece of local knowledge that mattered, the knowledge Japanese coastal villages had paid for over centuries and encoded in stone markers and village lore. When the ground shakes hard beside this ocean, the ocean is coming, and it comes more than once. The earthquake was the boundary doing exactly what we have spent this whole video describing. Offshore, to the southeast, the locked interface between the Pacific Plate and the Kamchatka margin let go along hundreds of kilometres, the segment immediately north of tonight's gap, the same neighbourhood the catalogues now describe in terms of distances from this very town. Modern reanalysis puts the magnitude between 8.8 and 9.0, which is to say, the same class of event as July 2025 on the adjoining stretch of the same arc within the lifetime of people still living today. The shaking in Severo-Kurilsk was violent enough to wake the town, damage buildings and drive people into the pre-dawn cold. And here the residents did something that speaks well of their instincts. Many of them, uncertain but unsettled, climbed. They moved up the hillsides behind the town and waited in the dark to see what would happen. It is worth dwelling for a moment on the knowledge these settlers did not have, because its absence is the quiet villain of this whole story. Across the strait to the south, Japanese coastal culture had spent centuries compiling exactly this lesson at exactly this kind of shoreline. Villages along the Sanriku coast, the stretch that would later face the 2011 disaster, maintained stone tablets on the hillsides, some over a century old even then, carved with instructions that read like messages from the dead to the living. Remember the calamity of the great tsunami. Do not build below this point. When the earth shakes, seek high ground and do not return. Do not return. The tablet carvers knew about the second wave because their grandparents had been killed by second waves. That accumulated, blood-bought coastal literacy was regional, cultural and utterly non-transferable through a war and a population exchange. When the Soviet Union replaced the Kuril's Japanese population after 1945, it replaced them with families from inland Russia and Ukraine, farm country, river country, people to whom the sea was scenery, and an earthquake was a thing that damaged buildings and then was over. The hazard stayed. The knowledge left. 7 years later, the bill for that mismatch came due in a single morning. What happened, roughly 3/4 of an hour after the shaking, was the first wave. It came ashore in the darkness, flooded the low-lying blocks of the town, did real damage, and then it withdrew. And from the hillsides, in the first grey light, the people of Severo-Kurilsk looked down at their soaked, battered, but still recognisably standing town, and they made the decision that turned a disaster into an annihilation. They went back down. You have to inhabit the decision honestly, because from the hillside in the cold it did not look like a mistake. It looked like the aftermath. The sea had come and gone. Down there were their homes, their stoves, their dry clothes, their documents, their savings, their children's things. Some went to look for family members, some went to salvage, some, reportedly, simply went back to bed. Nobody in an official capacity told them to stay on the hill, because there was no warning system, no tsunami education, no institutional memory. The state that governed them had held these islands for 7 years and had built no infrastructure for this moment whatsoever. And the ocean, meanwhile, was doing what tsunamis always do, the physics we walked through earlier tonight, oscillating. A tsunami is not one wave. It is a series, sometimes hours long, and the first arrival is frequently not the largest. The water that had flooded the town was the opening movement. The main force was still out there, in the strait, reorganizing. The second wave arrived while the town was full of people again. Survivor accounts and later reconstructions put it at roughly 15 to 18 meters, a 5 to 6 story building of ocean arriving at speed into a settlement of 1 and 2 story wooden structures on a low coastal flat. It did not flood Severo-Kurilsk. It removed Severo-Kurilsk. Buildings were lifted whole off their foundations and carried or disintegrated where they stood. The harbour installations, the processing plant, the garrison facilities, the homes, the wave took the town's entire physical existence and redistributed it across the strait and the lowlands. People who had climbed the hills a second time watched it happen beneath them. People who had not, the ones in the streets, in their doorways, in their beds, were part of what the water carried. A third wave followed, smaller, worrying the wreckage. When the sea finally settled, the flat ground where the district capital had stood that morning held foundations, debris, and mud. Contemporary accounts describe survivors wandering the hills in nightclothes in the November cold, and military aircraft beginning to arrive through the day to lift them off the island. Why is the second wave so often the killer? The physics deserves one more beat here, because it converts the tragedy from bad luck into pattern. A tsunami source the size of a 1952 rupture does not produce a pulse. It produces a wave train, a series of crests separated by tens of minutes, generated by the complex geometry of the seafloor displacement, and then modified by every reflection and resonance between the source and the shore. Straits, shelves, and harbours ring like struck bells, water sloshing on their own natural periods, and the interference between the incoming train and those local oscillations means the largest crest can arrive second, third, or fourth, an hour or more after the first. The first wave at Severo-Kurilsk was the leading edge of the train, not its peak. 40 minutes of apparent calm between waves is not the ocean finishing, it is the ocean reloading. Every modern tsunami advisory on Earth now carries language built directly on mornings like this one. Warnings remain in effect for hours. The first wave may not be the largest. Do not return until officially cleared. Each of those clauses is a headstone. The people on the hillside in 1952 were not foolish. They were simply the last generation on that coast to face the wave train without the sentence that describes it. The same waves raked the whole northern district that morning. Fishing settlements on Paramushir and Shumshu, camps and stations along the southeastern Kamchatka coast, some of which were simply never rebuilt, their names retired from the map. The total geography of destruction ran along hundreds of kilometres of coastline facing the rupture, the same span of coast that the 2025 survey teams would walk 73 years later, measuring run-ups of 10, 16, 19 metres against mostly empty shores. 1952 is what those same numbers do to shores that are not empty. It is the completed experiment. The control group and the test group run on the same arc, one lifetime apart. The wave did not stay in Russian waters either, and the far-field record is part of how the event's true size was later reconstructed. The 1952 tsunami crossed the Pacific just as its 2025 successor would, and it announced itself most loudly in Hawaii, where the water arrived hours later still carrying enough energy to flood low-lying areas, wreck boats, throw a cement barge around Honolulu harbour, and cause damage across the islands, remarkably, without taking a single life there. Tide gauges as far away as California and Peru recorded the passage. To the warning centres of the era, the Pacific Tsunami Warning System existed in embryonic form, built after the 1946 Aleutian tsunami had killed more than 150 people in Hilo. The instrument said plainly that something enormous had happened off Kamchatka. The world's seismographs had registered a top 5 earthquake. The world's tide gauges had registered its ocean-crossing wave. The event was, in the scientific sense, fully public. What was not public, what the instruments could not report, was the human accounting on the coastline nearest the source. The physics broadcast itself across an entire ocean. Only the deaths were classifiable. How many people died in Severo-Kurilsk and the surrounding settlements on November 5, 1952? Here is the terrible thing, the thing that turns this from a tragedy into something darker. To this day, nobody knows. And the reason nobody knows is not that the records were lost. It is that they were locked away on purpose by a government that decided within days that the destruction of one of its towns by the Pacific Ocean was a state secret. What happened next, the silence, the sealed numbers, the decades of official nothing, is its own part of this story, and it is the part that makes 1952 matter most for the questions we're asking tonight. Part 8. The Disaster That Never Happened. Open a Soviet newspaper from the second week of November 1952, and you will find the ordinary news of a superpower, industrial reports, party congresses, the amiable churn of official life. What you will not find, anywhere, is the news that a wave the height of a 6-story building had just erased a district capital of the Soviet Union and an unknown number of its citizens. There was no announcement. There were no casualty lists, no appeals for aid, no memorial editions. The disaster was classified, treated in the machinery of the Stalinist state, the way one would treat a failed weapons test or a military catastrophe. The survivors were evacuated, dispersed, and processed under conditions in which asking questions in public was unwise. Many were resettled far from the islands. The dead received no public accounting. For the citizens of the country in which it happened, the destruction of Severo-Kurilsk was, in the fullest bureaucratic sense, an event that had not occurred. The official figure, when it finally surfaced from the archives decades later, was 2,336 dead. Even taken at face value, that number would make this among the deadliest tsunamis in the recorded history of the Pacific. But it cannot be taken at face value, and the reasons are structural. The figure emerged from a state with every institutional incentive to undercount, in a district whose true population was itself partly opaque. A military frontier zone, 7 years into resettlement, with garrisons whose strengths were secret, seasonal workers who were nowhere permanently registered, and settlements small enough to vanish from paperwork when they vanished from the earth. Later researchers and journalists working from archival fragments, survivor testimony, and population reconstruction have argued the true toll ran far higher. Commonly cited estimates reach 8,000, and some run to 14,000. The spread between the official number and the high estimates is not a rounding disagreement. It is a factor of 6. Thousands of human beings exist inside that uncertainty. People whose deaths were real, whose names were known to someone, and whose fate was converted by policy into statistical fog. The deadliest tsunami in Russian history has no agreed death toll, and at this distance it almost certainly never will. The secrecy did not just hide the disaster, it permanently destroyed the ability to measure it. Why hide it? The logic, reconstructed from the era, is as mundane as it is chilling. The Kurils in 1952 were a closed military frontier at the coldest moment of the Cold War, 7 years after being taken from Japan, garrisoned against an American Pacific presence just across the water. Admitting the destruction of the district capital meant admitting the size and disposition of the garrison that had been destroyed with it. It meant admitting that a newly annexed, strategically sensitive territory had been settled onto killing ground with no protective infrastructure whatsoever. And beneath the strategic calculations sat the deeper reflex of the Stalinist state. Disasters were treated as admissions of weakness, and admissions of weakness were not made. The same machinery that suppressed famine numbers and accident reports processed a tsunami without friction. There was no need for a special decision, no dramatic cover-up meeting. The system simply did to Severo-Kurilsk what it did to everything. It filed it where no one could read it. And yet, and this is the strange, almost redemptive twist buried in the archive, the state that hid the disaster also acted on it. Within 4 years, the Soviet Union established a dedicated tsunami warning service for its Pacific coast, built on seismic stations and coastal observation posts across Kamchatka, the Kurils and Sakhalin, with protocols for sounding alarms in exactly the towns the 1952 waves had destroyed. The service dates to 1956, and it exists as a direct institutional consequence of the event its own government would not name. Think about what that pairing means. The state understood the lesson perfectly, well enough to spend money on sirens and stations and around-the-clock watch rosters. It simply declined to share the lesson with its own people, who were left to wonder what the new sirens were for. Protection without information, the machinery of warning, built atop the silence about why warning was needed. It may be the purest expression on record of a government's belief that safety is an engineering problem, while truth is a liability. It took roughly 4 decades for the story to reach the public in any full form. Only in the late Soviet period, as the archives cracked open, did accounts of November 5, 1952 begin to circulate. The hillsides, the return, the second wave, the airlift, the silence. By then, the town itself had long since been rebuilt, and rebuilt differently. The new Severo-Kurilsk was sited with the lesson in mind, its centre pulled back and up from the shoreline that had killed its predecessor. That reciting is why, when the 2025 tsunami drove 19 metres of run-up onto the northern Kurils, the modern town, warned by a functioning system, sheltered by geography its founders bought with their lives, came through. The 1952 dead are, in the most literal sense, the reason the 2025 toll was what it was. Every disaster is a tuition payment. The question a society answers afterward is, who is allowed to see what the tuition bought? Set the two information regimes side by side, because the contrast is the hinge on which this whole video swings. 2011 Japan. A magnitude 9.1 ruptures the next boundary segment south of the Kurils, and within minutes the entire planet is watching. Live helicopter feeds of the wave crossing the Sendai Plain, automated alerts on tens of millions of phones, casualty figures updated hourly in public, every seismogram and tide gauge reading published to open databases where researchers from every country on Earth still mine them today. 2025 Kamchatka. Same transparency, delivered even faster, and the ocean's arrival was measured by public sensors before it reached most coasts. 1952, the same arc as 2025, one segment north of 2011's, an event of the same physical class as both, and the total public record at the time consisted of foreign seismometer readings and rumours, 3 great earthquakes, 3 neighbouring segments of one plate boundary, and the death tolls scale not with the size of the waves, but with the openness of the societies they struck and the warning those societies had built. That is the actual lesson of this arc, and it is not a geological lesson at all, and that is why this town anchors tonight's video, rather than merely haunting it. Remember what the map in Part 6 showed. This weekend's northern cluster is catalogued in kilometres from Severo-Kurilsk. The town sits at the hinge between the segment that broke in 1952, the segment that broke in 2025, and the gap to the south that has not broken in the modern record. It has already stood at this exact intersection once, beside a loaded boundary, in the path of whatever the boundary does next, and the institutions responsible for it at the time chose darkness. No warning before, no truth after. Tonight it stands there again. The boundary is loaded again. This weekend's earthquakes are sketching geometry around the gap again, and the difference, the entire difference, is the information environment. Open catalogues instead of sealed archives. Public censors instead of state secrets. A global system that, 13 months ago, proved it could see this arc rupture in real time and move whole coastlines out of the way. Which raises a question we're obligated to take seriously, precisely because this story makes it reasonable. If a government hid a disaster this size once, how confident can you be that the picture you're being shown today, the catalogues, the maps, this weekend's tidy list of magnitude 4s, is complete? People are asking a version of that question right now, in real time, about this very dataset, and they are pointing at gaps between what the seismographs show and what the public feeds list. We are going to answer it properly, with the actual mechanics of how earthquake catalogues are built, later tonight. But before we do, we need to finish reading the present moment, because the strangest feature of this weekend was not the earthquakes at all. It was everything else. While one arc chattered, the rest of the planet fell almost silent, and that silence is a data point in its own right. Part 9. The quiet, everywhere else. Some weeks the Earth is loud everywhere, and a busy catalogue is just a busy catalogue. This was the opposite kind of week, and the opposite kind is rarer and more interesting. Pull back from the Kurils and survey the whole planet's seismicity for the window around this burst, and the picture is one of broad, conspicuous calm. The rolling 7-day count of earthquakes at magnitude 4.5 and above came in at 126, down from 150 the week before, a 16% drop in the global rate, and the top end of the distribution thinned even more than the count suggests. The largest earthquake on Earth in the window was a magnitude 5.2 beneath central Peru, and that event at roughly 130 kilometers deep was an intraslab rupture inside the subducted Nazca plate, the kind that rattles windows across a wide region and threatens almost nothing. Beyond it, a magnitude 5.1 south of Tonga, shallow, remote, unremarkable. A magnitude 5.1 south of Fiji, 149 kilometers deep. A magnitude 5.0 near Suez in Egypt, notable mainly for its unusual address. And that is the complete global roster above magnitude 5, no 6 anywhere, days without one. The rest of the roster only deepens the impression of a planet murmuring rather than speaking. A magnitude 4.7 in Morocco, shallow, in the Atlas mountain country that produced the deadly 2023 earthquake, felt, noted, harmless. A magnitude 4.5 near Sanchez in the Dominican Republic, on the perpetually grinding northern Caribbean boundary. A pair of magnitude 4.9s in eastern Sichuan, China. A 4.6 deep beneath Argentina. Scattered 4s along the Middle America Trench off Chiapas, the decaying tail of the magnitude 7 class sequence there from mid-July, the one we covered in our videos from the 18th and 19th of July, still obeying its decay curve like a well-behaved textbook example. Every one of these is ordinary. Together they make the point. The planet's boundaries were all present, all accounted for, all idling, except one. For perspective, the planet's long-run average serves up well over a magnitude 6 somewhere every week of the year, and the running 2026 pace had been tracking normal ranges, which makes a stretch this quiet a genuine statistical lull, the kind that shows up a few times a year and always unsettles the people who watch these feeds daily. Daily catalogue watchers describe the same window in their own terms: total released seismic energy running at a fraction of an ordinary day, whole regions that usually contribute steady moderate activity. The Philippines trench systems, the the New Zealand region, the South American margin, all idling at once, producing threes where they usually produce fives. The energy arithmetic behind that impression is worth making explicit, because it explains how a week with 126 catalogued earthquakes can still count as silent. Earthquake energy is so steeply logarithmic that the biggest events do not lead the ledger, they are the ledger. 1 magnitude 6.0 releases about as much energy as 32 magnitude 5.0s, or roughly 1,000 magnitude 4.0s. In a normal week, a single magnitude 6 somewhere on Earth carries the vast majority of the planet's released seismic energy, and everything below it is accounting dust. Remove the 6s entirely, as this week did, and cap the distribution at 5.2, and the total energy release collapses to a few percent of a typical week, no matter how many 4s fill the list. One daily observer who tracks a self-built global energy index on a 10-point scale, where a normal day runs around 4 or 5, described the readings through this window dropping to 1.7 and then 1.1. The scale is informal, but the physics underneath it is not. Measured by energy rather than by count, the planet effectively went still. Which makes the one place that did not go still, the arc we have spent this whole night on, carry nearly the entire signal by itself. Let me head off the two wrong conclusions that this kind of quiet always generates, because they arrive in every comment section within hours and they point in opposite directions. Wrong conclusion number 1. The quiet is safety. The planet is calming down. It is not, because it cannot. The engines do not idle. The Pacific Plate consumed its 80 millimeters against the Kuril margin this week, exactly on schedule, quiet or loud. Strain accumulation is a function of plate motion, and plate motion does not take weeks off. A quiet week means the release side of the ledger paused while the deposit side kept running, which means, with the cold arithmetic of a fault system, that the planet ended this quiet week carrying marginally more stored energy than it started with. Wrong conclusion number 2. The quiet is a countdown, the calm before the storm, the planet holding its breath. Also unsupported. Decades of statistical work have hunted for a reliable relationship between global lulls and subsequent great earthquakes, and the honest verdict is that no such predictive relationship has survived scrutiny. Lulls happen. They end. Usually they end with the return of ordinary background, not with catastrophe. The quiet is neither a blessing nor a fuse. It is variance. But here is what the quiet genuinely is, for our purposes: contrast die. Against a loud planetary background, 7 moderate earthquakes on one arc would be statistically invisible, a regional detail swallowed by noise. Against this background, the Kuril burst stands out the way a single lit window stands out on a dark street. The signal-to-noise ratio of this weekend was, by luck of timing, close to ideal, and that is the only reason a channel like this one can even attempt the analysis we have been doing tonight. When the whole street is lit, you cannot tell which window matters. This week the street went dark and one window stayed lit, and it happened to be the window we already had reasons to watch. The quiet extended overhead too, and this matters because of a theory that will otherwise fill the comment section. The sun, during this exact window, was as close to inert as it gets in the middle years of a solar cycle. X-ray output flatlined in the lowest observable class, no significant flares, no Earth-directed eruptions, the planetary geomagnetic index bottoming out at values near 0.67, a level representing an essentially undisturbed magnetic field. Solar wind drifted past at about 400 kilometers per second, the baseline breeze. Auroral power idled at 12 gigawatts per hemisphere, the dimmest of pilot lights. I lay this out because a persistent online tradition holds that solar activity triggers large earthquakes, that flares and geomagnetic storms stress the crust electromagnetically and shake loose events that were waiting. The theory has been tested against a century of catalogues, repeatedly, and no robust correlation has survived. But this weekend supplies something better than a literature citation. It supplies a clean natural experiment. Whatever organised 7 earthquakes onto one arc during one of the quietest space weather stretches of the year, it was not the sun, because the sun was not doing anything. The driver was where it always was, 80 millimeters a year of Pacific Plate and a 500-kilometer scar from last July, redistributing its load through the rock. So the quiet sharpens the question rather than answering it. One boundary active while the planet idles, 2 clusters framing a loaded gap, a mechanism, stress transfer, fully capable of explaining the geometry, and a base rate insisting that most such patterns dissolve into nothing. Before we weigh all of that in the balance, though, the map has one more layer, and it is a layer most earthquake coverage never draws. The Kuril arc is only the western edge of the object in question. The object is the Pacific Plate itself, a single mechanical body larger than any continent, and this same weekend its other edges were talking too. From the Aleutians to the coast of Oregon, a chain of smaller signals traced the rest of the plate's outline, and at least one of them has been building for months. That is where we go next. Part 10. The Other Edges of the Plate. The Pacific Plate is the largest single object on the surface of the Earth, and this weekend 3 of its other edges were making noise at the same time as the Kurils. That sentence needs immediate discipline. Correlation between distant boundaries is where earthquake analysis goes to die, and we will apply the discipline in a moment. But the observations themselves are real. They are part of the same weekend's record, and several of them connect to stories this channel has been tracking for weeks. So let us walk the plate's rim, briefly, edge by edge. Start at the top of the map, along the Aleutian Arc, the plate's northern boundary, where it subducts beneath Alaska. The monitoring feeds show a cluster in the Andreanof Islands region that has now been simmering for months. Daily catalogue watchers put it on the order of 140 earthquakes in the past month alone, mostly in the magnitude 3 and 4 range, punctuated earlier this year by a magnitude 6.4, with a described texture of deeper events followed by shallow adjustment, the slab working at depth, the upper plate answering above. If that region sounds familiar, it should. Our video from July 26th was devoted to the central Aleutians, the Atka volcanic complex, the Andreanof doublet of late July, and the uncomfortable fact that the most volcanically active region in the United States is watched by a network that clouds routinely defeat. The cluster has continued since that video. The same island group produced a magnitude 8.6 in 1957, so the ceiling here is not hypothetical, and the informal threshold we set in that video still stands. This story escalates if the cluster crosses a reviewed magnitude 6 or migrates up dip toward the trench. It has done neither yet. It simply has not stopped either. The 1957 precedent deserves its 30 seconds because it completes a pattern you will have noticed by now. On March 9th of that year, the Andreanof segment produced a magnitude 8.6, one of the largest American earthquakes of the 20th century, and its tsunami crossed the Pacific to strike Hawaii, wrecking bridges and boats and flooding coastal communities, 5 years after the 1952 Kamchatka wave had done the same, and 11 years after the 1946 Aleutian wave had killed more than 150 people in Hilo and forced the creation of the Pacific Warning System in the first place. 3 of the mid-century Pacific's great tsunamis, all sourced from the same northern rim of this same plate, all arriving on the same distant islands. The northern boundaries, Aleutian and Kuril alike, are Hawaii's problem, and California's and Japan's, because the ocean between them is not a barrier. It is a transmission line. That is the standing reason a months-long swarm in the Andreanovs belongs in any serious weekly picture of Pacific hazard, even at magnitude 3 and 4. The arc it sits on has already proven, within living memory, what its product looks like on delivery 5,000 kilometers away. The volcanic side of the Alaska boundary is flying its own quiet flags this week, and they complete the picture of a plate edge fully awake. Great Sitkin, the island volcano in the same Andreanof group, remains at aviation code orange, watch status, where it has sat for years now as lava slowly fills its summit crater, the longest-running eruption in the Aleutians. 4 other American volcanoes hold yellow advisory status this week. Kupreanof and Shishaldin along the same arc, Kilauea in Hawaii, and the Ahi Seamount far to the west in the Marianas. None of that is alarming in itself. Elevated statuses along the Aleutians are closer to normal than not. But recall the frame from the beginning of tonight. Earthquakes are the drive train, and volcanoes are the exhaust of the same subduction engine. Along the Alaska rim this week, both are running warm at once, on the same arc where the earthquake swarm will not quit. Same machine, both gauges off their pins, and nobody watching except the people who watch everything. Now run down the plate's eastern rim. Off the coast of British Columbia, the feeds logged a magnitude 4.8 on the morning of August 3rd, sitting north of the Explorer Plate region, the small dying fragment of ocean floor whose slab tears and strange seismicity we mapped in our video from July 20th. The location matters because late July produced a burst of activity within the Explorer region itself, and a new moderate event to its north reads, at minimum, as the same corner of the plate boundary system continuing to adjust. Farther south, on the Blanco fracture zone, the transform fault connecting the Gorda Ridge system toward the southern end of Cascadia, a magnitude 4 class event, unremarkable alone, notable mainly for its address. Blanco events bracket the quiet southern Cascadia margin, whose rising tremor counts we examined in our video from July 25th, and Cascadia itself in the current interval is running a tremor count of 81 epicenters, concentrated toward the northern end of the margin, the slow, silent, deep slipping that loads the locked zone above it, ticking along in the background exactly as it was 3 weeks ago. Here is what all of that is, and here is what it is not. It is one mechanical body, a single plate, 60 million square kilometers of it, being worked at its northern, eastern and western boundaries in the same window, with each boundary expressing the stress in its own local vocabulary. Swarms in the Aleutians, fragment adjustment off Canada, silent tremor under Cascadia, and our clustered fours along the Kurils. It is a reminder that the plate is not an abstraction. The same slab of rock that dives beneath Severo-Kurilsk runs unbroken to the seafloor off Oregon, and its motion budget is global. What it is not, and I want this stated as plainly as the physics allows, is a chain reaction. Static stress transfer, the mechanism this whole video runs on, dies with distance. It is a local phenomenon, meaningful across tens to a few hundreds of kilometers, utterly negligible across the 5,000 kilometers separating the Kurils from Cascadia. An earthquake in the Kurils does not load Oregon. Dynamic triggering, the passing seismic waves of truly great earthquakes jostling distant faults into activity, is real, but requires a great earthquake, and nothing this weekend came within 2 orders of magnitude of qualifying. The simultaneity of the plate's murmuring edges is not causation. It is the ordinary state of the fastest-moving large plate on Earth, made visible, like everything else this weekend, by the global quiet behind it. So file the plate tour where it belongs, context, not evidence. The Aleutian cluster is its own story with its own thresholds. Cascadia is its own story, on its own clock. The signal of this weekend, the thing that organized, the thing with geometry, the thing wrapped around a known loaded gap, remains exactly where we left it, on the arc between Kamchatka and Japan. And the honest next question about that signal is the one we have been circling all night. Everyone from the catalogue watchers to the warning centres is now, in some sense, watching the gap. So what precisely can watching accomplish? What can the instruments of 2026 actually see coming? And what, despite every satellite and sensor and open database, remains as invisible today as it was to the sleeping town of Severo-Kurilsk? That is part 11, and it is where this video tells you the truth most earthquake coverage is built to avoid. Part 11. What the instruments can actually prove. The truth is this: nobody on Earth can predict an earthquake, and the failure is not for lack of trying. For roughly half a century, prediction, a date, a place, a magnitude, in advance, reliably, was a serious scientific program in the United States, Japan, the Soviet Union, and China. Money was spent at national scale. Every plausible precursor was chased: foreshock patterns, ground tilt, radon gas seeping from wells, electrical signals in the crust, animal behavior, groundwater changes, seismic velocity shifts. Each candidate produced tantalizing case studies and then failed the only test that matters, working consistently in advance more often than chance. The sobering consensus that emerged, and that still stands, is that the nucleation of a great earthquake may be inherently unobservable. The difference between a patch of fault that slips into a magnitude 4 and 1 that keeps tearing into a magnitude 9 may not exist until the rupture is already running. The fours we catalogued this weekend and the great earthquake this video has been circling may begin identically. The rock itself may not know which one it is having until it is having it. 2 famous episodes bracket the whole history of the prediction dream, and they are worth knowing because together they killed it. The first is Haicheng, China, February 1975. A rising foreshock swarm alarmed authorities into evacuating a city of 1 million people, and when a magnitude 7.3 struck hours later, collapsing buildings across the region, the death toll was a fraction of what it should have been. it remains the only large earthquake in history plausibly predicted in a way that saved lives, and it minted a generation of optimism. 17 months later, the same country, the same agencies, the same methods faced Tangshan. No foreshocks, no anomalies that anyone flagged in time, no warning of any kind. The magnitude 7.6 that struck that sleeping industrial city in July 1976 killed at least 240,000 people. By the official count, estimates run far higher, in one of the deadliest earthquakes in human history. Same tools, same experts, opposite outcomes, because Haicheng's earthquake had happened to announce itself, and Tangshan's had not. The second episode is Parkfield, California, where a stretch of the San Andreas had produced moderate earthquakes so regularly, roughly every 22 years, that the United States formally predicted the next one for a window in the late 1980s and instrumented the fault like an intensive care patient to catch it. The earthquake ignored the window by more than a decade, arriving unannounced in 2004, precursor-free, recorded in exquisite detail by instruments that saw nothing coming until it came. Read together, the lesson is brutal and clean. Sometimes the fault talks first, and sometimes it does not, and nothing yet discovered tells you which kind of fault you are standing on. That is why the statistics we keep citing are phrased the way they are. When an earthquake occurs anywhere, the probability that it turns out to be the opening act of something larger within the next few days runs around 5 to 6%, a number that holds with eerie stability across regions and decades. 19 times out of 20, a cluster like this weekend's is complete in itself. The label foreshock is only ever awarded in retrospect, by the main shock that follows. This is not a hedge. It is the entire honest content of earthquake forecasting at short timescales, and any voice, on the internet or on television, who tells you a specific large earthquake is coming this week is lying or guessing, with no third option. But the story does not end in helplessness, because prediction was never the only game, and the things the instruments can do have quietly become extraordinary. Forecasting, probabilities over years and decades, works. It is why we can say the gap segments carry elevated hazard, why building codes in Japan and Chile and Alaska are written the way they are, why the aftershock forecasts published after the 2025 main shock performed almost embarrassingly well. Rapid characterization works. Within minutes of any significant rupture on this arc, global networks locate it, size it, and resolve its mechanism. Within a quarter hour, tsunami centers have modeled the wave. The DART sensors then measure the actual ocean in transit and correct the model in real time. Earthquake early warning works within its physical limits. Seismic waves outrun nothing but themselves, so a network that detects a rupture's first seconds can radio ahead of the strong shaking, and buy seconds to tens of seconds for the surrounding region, enough to stop trains and open firehouse doors, though never enough for the town directly above the epicenter. And geodesy, the satellite positioning networks measuring the slow warp of the crust in millimeters per year, can watch strain accumulate on the locked zones between earthquakes, which is precisely how we know the gap is a gap, the measurement of what has not yet been spent. So apply the toolkit to our specific question, and the shape of the coming weeks resolves into a checklist. The instruments cannot tell us whether the gap will rupture soon. They can tell us within days what this weekend actually was. The reviewed moment tensors will come, and they will say interface or intraslab, locked boundary or bending slab. The catalogue will say whether the clusters decay on an aftershock-like curve, hold steady as swarms or migrate. And migration toward the quiet centre, from either end, is the single most important spatial signal available. Magnitudes will say whether the burst stays in the 4s or escalates. A magnitude 5.5 or larger with a thrust mechanism between the clusters, inside the gap itself, would move this story instantly from pattern watching to event coverage on every wire service on Earth. And if the worst case arrives, if the gap goes, at whatever hour on whatever day it chooses, the instruments will do what they did in 2025, see it in seconds, warn an ocean in minutes, and hand every coastline in the Pacific the choice that Severo-Kurilsk never got. That is what watching accomplishes, not prophecy, preparation with a shorter fuse. Apply one more instrument to our arc specifically, because it is the one that will eventually write this story's ending whether or not any of us are still watching, the satellite positioning networks. Permanent geodetic stations on Kamchatka, the Kurils, Hokkaido, and the islands of the North Pacific measure their own positions continuously to millimetre precision, and from the slow, patient warping of that station web, researchers resolve which patches of the plate interface are locked and which are creeping. Locked patches drag the coastline above them landward and downward, year after year, at rates the stations record like a ledger. This is the deep answer to how anyone can claim to know the gap is loaded. The land itself is visibly bending around the locked segments, and has been for as long as the measurements run. After the 2025 earthquake, the same network measured the rebound. Coastal stations lurching seaward by meters above the rupture, the bent beam springing back, and mapped where the springing stopped. Where it stopped is the gap. In the months and years ahead, those stations will report one of two things about the segments to the south. Continued steady bending, meaning continued loading on a locked boundary, or something stranger, an acceleration, a slow slip transient, a creep event relieving strain quietly. Either report will be public within days of the data existing. The gap cannot move, or even meaningfully creak, without a web of instruments in 4 countries writing it down. There is one more piece of the epistemics to settle, though, and it is the piece this story uniquely forces. Everything in this part assumes the data reaches you, that the catalogues are honest, the feeds complete, the numbers unmassaged. This video has already shown you a government that broke that assumption at the cost of thousands of lives. And right now, in the comment sections and forums where people watch these same feeds nightly, a quieter version of the same suspicion is circulating about the present. The claim that the catalogues are being curated, that earthquakes visible on the public seismographs are missing from the public lists, that what you're shown is less than what is known. Some of the people saying this are pointing at real discrepancies. They deserve a real answer, and the real answer is more interesting than the suspicion. That is Part 12. Part 12. The Missing Earthquakes. Watch the raw feeds long enough, and you will see it for yourself. A seismograph station near a known cluster zone draws 3 sharp spikes in an hour, and the public catalogue lists 1 earthquake. People who monitor these stations nightly document cases like this constantly. A spike on the drum with no corresponding entry, a swarm visibly rippling across a regional network while the official list shows a single event per day, small earthquakes felt and reported by residents that never appear at all. From there, the inference feels short. If they do not list what the instruments plainly recorded, the catalogue is curated, and if it is curated, what else is being withheld? The suspicion is not stupid. It is built on accurate observations of real gaps. It just gets the mechanism wrong, and walking through the actual mechanism is worth 10 minutes of a 2-hour video, because catalogue literacy is the vaccine for a whole family of internet seismology. The first concept is the detection flaw, what seismologists call the magnitude of completeness. No network records every earthquake. Below some magnitude, events are too small to be reliably detected, located, and distinguished from noise by the available stations. And that flaw varies enormously from place to place, because station density varies enormously. Southern California, with hundreds of instruments packed around its faults, catalogues events below magnitude 1, which is why its public lists brim with tiny quakes, 0.5s, 0.8s, and apparent hyperactivity that is really just excellent hearing. The remote North Pacific is the opposite case. For the open ocean stretches of the Kuril arc, the practical floor for reliable global cataloguing sits in the high 3s to mid 4s. An event the regional Russian or Japanese stations can see on their drums may simply not meet the global network standard for a confident reviewed location. Same planet, different microphones. The 3 spikes 1 listing pattern is the floor, not a filter. The second concept is review. Modern catalogues are 2-stage. Automated systems post preliminary detections within minutes, and human analysts then confirm, refine, or delete them. Automated picks in noisy or sparsely instrumented regions are wrong constantly. Phantom events assembled from unrelated noise, single quakes split into 2, 2 quakes merged into 1, magnitudes off by half a unit. The reviewed catalogue is deliberately conservative because it is the version researchers build science on, and its standards are published, versioned, and public. That conservatism produces exactly the visible symptoms the suspicious point at. Events appearing hours late, magnitudes revised, preliminary entries vanishing. And the third concept is simply plurality. There are multiple independent catalogues, the United States Geological Survey, the European Mediterranean Seismological Center, the Japanese Agency, the Russian Academy networks, and others, run by different institutions in different countries with different thresholds and different review policies. They disagree at the margins every single day. The disagreement is not leakage from a cover-up. It is what independent measurement looks like. If the lists all match perfectly, that would be the tell. There is also a fourth concept, newer than the others, that has quietly transformed who gets to check the checkers: the amateur sensor web. Over the past decade, thousands of hobbyists, schools, and enthusiasts around the world have installed small, inexpensive seismographs, consumer devices built around the same sensing principles as professional instruments, and networked them into public real-time maps. The consequence is that the raw ground truth is no longer even nominally an institutional monopoly. When a moderate earthquake strikes anywhere near populated ground, hundreds of privately owned instruments record it, timestamp it, and publish it, independent of any agency, before any official review completes. Alongside them run the crowdsourced felt report systems, public portals where anyone who feels shaking logs it, generating intensity maps from thousands of testimonies within minutes. An earthquake big enough to matter is now witnessed simultaneously by government networks, rival foreign networks, private hardware in living rooms, and the nervous systems of everyone standing on top of it, all writing to the public record at once. Whatever one thinks of any single institution, the architecture as a whole has become structurally incapable of keeping a significant earthquake secret, which is precisely the standard against which the strong version of the suspicion should be tested. But let us take the strong version of the claim seriously, because this video has earned the right to. Suppose an agency wanted to hide significant earthquakes from you, not drop sub-threshold 4s, but conceal events that matter. Could it? Here the 1952 comparison stops being rhetorical and becomes a controlled experiment, because we know exactly what successful concealment required. It required a closed state with a monopoly on instruments inside its borders, a press that printed nothing unapproved, survivors who could be dispersed and silenced, and a foreign scientific community that could see the seismogram but not the shoreline. Every one of those conditions has been abolished by the modern architecture. Today, a significant Kuril earthquake is recorded simultaneously by networks in at least 4 countries that do not answer to each other, posted to public feeds within minutes, cross-checked by amateurs running their own instruments. The global community of hobbyist seismograph operators is real and growing, and, if it moves the ocean, measured by dart sensors whose data streams are public by design. To hide one earthquake would require synchronized suppression across rival governments, thousands of independent scientists, and an open sensor web, a conspiracy whose cost would exceed any conceivable benefit, deployed to conceal information that the bad actor of 1952 ultimately could not keep sealed even with every advantage a totalitarian state possessed. The Soviet Union hid the deaths. It never managed to hide the earthquake. The seismograms crossed the border at the speed of shear waves, and the tide gauges of Hawaii took the wave's confession hours later. So here is the inversion, and it is the moral center of this entire night. The people worried about hidden earthquakes are right that the danger is real. They have simply misplaced it in time. Concealment is not a live threat in the catalogues of 2026. It is the documented historical crime of 1952, and the modern open data architecture is the civilizational answer to it, built deliberately, sensor by sensor and treaty by treaty, so that no coastline would ever again depend on a government's permission to know the ocean was coming. The catalogues you can check tonight from your phone, with their maddening gaps, their revisions, their disagreements at the margins, are not the descendants of the sealed archive. They are its refutation. And the sharpest way to honour the unnumbered dead of Severo-Kurilsk is to understand the difference. They were not killed by missing data. They were killed by a world in which the data belonged to the state. You live in the other world. The question this weekend poses, 2 clusters, 1 loaded gap, a quiet planet, is at least a question you are permitted to watch being answered. What then should you actually expect if the answer is the bad one? What does the gap failing actually look like hour by hour for the coastlines that ring the North Pacific? That is where we go next, carefully, with numbers instead of nightmares. Part 13. If the gap goes. Run the scenario forward, then, with the discipline this channel owes you, not a nightmare, a forecast product. built from what this same arc has actually done, at magnitudes it has actually reached, on segments adjacent to the one in question. Suppose the gap fails as its neighbours failed. Suppose that on some unremarkable day, a Tuesday in March, a night in October, 13 days or 13 years from now, the locked interface of the central and southern Kurils lets go along several hundred kilometres at the magnitude 8.5 to 9 class its dimensions and slip deficit could support. What actually happens, hour by hour, to the coastlines of the North Pacific? Minute 0 to minute 5, the rupture runs. Somewhere under the seafloor near the island chain, the tear nucleates and propagates along strike, exactly as its northern neighbour did in 2025. Several minutes of sustained tearing, tens of metres of slip in the worst patches, the seafloor above heaving. Every seismic network on the planet lights up before the rupture is even finished. Automated magnitude estimates begin converging on the answer within the first minutes, revised upward as the full duration becomes clear. The warning centres do not wait for precision. For an event of this class in this location, tsunami warnings for the near field go out essentially immediately. Minute 5 to minute 40. The near field pays first and pays most. This is the unavoidable truth of subduction tsunamis, unchanged since 1952. The coastlines closest to the source get the largest waves in the least time. The Kuril Islands themselves, the handful of settlements along the chain, the fishing stations, the border posts, would face wave arrivals within tens of minutes at run-ups that the 2025 survey teams have already calibrated for us. 5 to 10 metres typically, 10 to 16 where the coast focuses, and worse in the unluckiest pockets. Severo-Kurilsk, depending on where along the gap the rupture centres, faces the same drill its rebuilt streets were designed for: sirens, the climb, and the hope that the reciting bought in 1952's blood holds the margin it was drawn to hold. For the northern coast of Hokkaido and Japan's Pacific-facing northeast, arrival times run from roughly half an hour to an hour and a half, enough, with modern warning, for coastal Japan to execute the evacuations it drills relentlessly, not enough for anyone who ignores the sirens. The Japanese agency's warning framework, refined hard after 2011 when initial magnitude underestimates cost lives, now airs loud and early for exactly this class of source. Hour 1 to hour 10. The ocean distributes the bill. The wave crosses the Pacific at jet speed, and the arithmetic of great circle distances takes over. Hawaii, the islands that took damaging waves from this plate's rim in 1946, 1952, and 1957, sits roughly 6 to 7 hours from a Kuril source. Time for full-scale coastal evacuation and a test of whether people honour it. The west coast of North America follows in the 8 to 10 hour band, and if that seems abstract, this exact arc has already run the demonstration at moderate scale, within recent memory. The 2006 magnitude 8.3 in the central Kurils, the gap's own northern neighbour, the first of the twins from Part 5, sent a tsunami across the whole basin that, 8 hours later and 5,000 kilometres away, surged into the harbour at Crescent City, California, tearing up docks and causing millions of dollars in damage from a wave that had crossed the entire North Pacific. No one died. The harbour was wrecked anyway. That was a magnitude 8.3 from the smaller end of what the gap could plausibly host. The scaling from 8.3 to 8.8 is not 10%. It is more than fivefold in energy, and the far-field wave scales with it. And through all of it, this is the part worth holding on to. The deaths are not written by the wave height. They are written by the gap between warning and behaviour. The 2025 event proved the ceiling of the modern system. A top 6 earthquake, a 19-metre wave, and a minimal toll, because the sensors saw it, the centres called it, and the coastlines moved. 1952 proved the flaw. The same class of event, unwitnessed and unwarned, and thousands gone into a sealed archive. The gap failing tomorrow would be neither. It would be a live experiment somewhere between those two proofs, its outcome decided by sirens maintained or neglected, drills rehearsed or skipped, and by however many people on however many shores remember, in the moment the sea pulls back, that the first wave is not the last and the hillside is not optional. The wave is physics and the physics is settled. The toll is civics, and civics is a choice made in advance. Hour 10 to week 2. The long tail, which coverage always forgets and coastlines never get to. A great subduction earthquake is not an event. It is the opening of a sequence. The aftershocks begin immediately and include, with high probability, multiple magnitude 7s, each one on any other week, a headline earthquake in its own right, each one near a coast already struck, capable of putting fresh water on wounded shorelines and re-triggering warnings for populations already exhausted. The 2006 Kuril event demonstrated the darker version of the tale. Its magnitude 8.1 outer rise twin arrived 59 days later, a second great earthquake from a structure the first had unclamped. And outer rise events, for all their distance from shore, are efficient tsunami sources in their own right because they break the seafloor vertically. Harbours across the Pacific would spend those weeks on a rhythm of assessment and rewarning. Surge damage tallied from the Kurils to Crescent City. Shipping rerouted around a North Pacific whose Great Circle lanes, the routes connecting Asia's ports to North America, pass directly along this arc. Aviation steering wide of any volcanic response the shaken arc might add. Insurance and reinsurance markets repricing an ocean. And on the empty coastlines nearest the source, the 2025 survey protocol would repeat. Teams walking the debris lines with instruments, measuring how high the water reached, converting catastrophe into the calibration data that protects the next generation. Every number in tonight's video that came from a survey team was once somebody's worst day, converted into everyone else's margin of safety. One more honest calibration before we close the scenario, because this channel does not deal in inevitabilities disguised as forecasts. Nothing in tonight's evidence says this rupture is near. The gap could fail next year. It could fail in 2080. It could fail in installments, a magnitude 7.8 here and 8.1 there, over decades, rather than as one giant. Sections of it may even creep more than the locked zone models assume and hold less stored slip than the worst case implies. Segmented boundaries keep their own counsel. What the evidence does say is narrower and harder. The segment is real. The loading is real and measured. The transferred stress from 2025 is real and permanent. The arc's habit of sequenced failure is documented twice over, and this weekend, for 36 hours, the seismicity of a quiet planet organized itself around that segment's edges like iron filings sketching a magnet nobody can see. You do not get to know the date. You get to know the shape. And knowing the shape, the only rational posture left is the one this channel was named for. You watch. Which brings us at last to exactly what watching means from tonight forward. The specific signals, in order, that will tell us what this weekend was. Part 14. The watch continues. Strip tonight down to what a careful observer should actually carry forward, and it fits on a single card. This weekend, 7 moderate earthquakes struck the Kuril-Kamchatka arc in 36 hours, while the planet's seismicity fell to one of its quietest weeks of the year. They formed 2 clusters, one at the southern edge of the 2025 magnitude 8.8 rupture, one at the far end of the chain near the Japan Trench handoff, and between them lies the section that rupture loaded and left unbroken. The pattern is consistent with stress adjustment around a loaded gap. It is equally consistent with ordinary arc seismicity, made visible by a quiet week. 10 data points cannot tell those stories apart. The next week's can, and here is the card that decides it. Signal 1. Anything moderate or larger inside the gap itself. The quiet center between the clusters is the watch zone. A magnitude 5.5 or larger landing between the latitudes of the 2 clusters, in the central Kurils, would be the single most significant possible development, and if its mechanism resolves as low-angle thrust on the interface, the loaded segment reading stops being an interpretation and becomes the leading hypothesis on the table. Watch the center. The center is the story. Signal 2. The moment tensors. Within days, the reviewed mechanisms for this weekend's fours will be published in the open catalogues. Interface thrust solutions for the shallow northern pair would tie the burst directly to the locked boundary at the rupture's edge. A spread of intra-slab bending solutions would downgrade the whole weekend to post-giant settling. A real and reportable answer, and if that is the answer, you will hear it on this channel stated just as plainly as tonight's questions. Signal 3. Migration. Clusters that decay in place are aftershock-like and boring in the best sense. Clusters that drift, north cluster extending south, south cluster extending north, either one reaching toward the quiet center, are doing something the aftershock model does not explain. The catalogues update continuously and publicly. A migrating front would be visible to anyone watching within days of it beginning. Signal 4. the neighbours, the Aleutian swarm crossing a reviewed magnitude 6, or the geodetic networks reporting anything anomalous from the Kuril stations, an acceleration, a slow slip transient, a creep event on the gap segments. Both would be published openly, the first within minutes of occurring, the second within days of the data processing. Neither requires anyone's permission to see, and if you live on the American side of this ocean, the card has a practical footnote, because the transmission line runs to your shore too. Hawaii and the West Coast sit hours downstream of any Kuril source, hours in which the entire warning apparatus works exactly as designed if the people it warns cooperate. The preparation is almost insultingly simple, and it is the same preparation this channel has named before for Cascadia and for the Aleutians. Know tonight whether your home, your work, and your school sit in a mapped tsunami zone. The maps are public, searchable, and free. Know the walking route to high ground, because roads jam and cars are where tsunami casualties concentrate in warned populations. And internalize the one rule that would have saved Severo-Kurilsk, the rule carved into Japanese hillside stones a century before it was needed again. When the warning comes, or the ground shakes long and hard near a coast, or the sea withdraws strangely, you go up and you stay up for hours, because the first wave is not the last. That is the entire syllabus. It costs an evening to learn, it is rehearsed by tens of millions of people around this ocean every year, and it is the one variable in tonight's whole story that you personally control. That is the whole discipline. 4 signals, all public, all checkable from anywhere on Earth with a connection. No prophecy, no countdown, no secret knowledge, just a defined watch zone and the patience to attend to it. It is precisely the discipline that was structurally impossible in 1952, when the instruments belong to states, and the states belong to their secrets, and it is the quiet inheritance this story leaves you. The boundary between the watchable world and the hidden one runs through time, not geography, and you are on the fortunate side of it. There is also a way to carry tonight that has nothing to do with this one arc, and it may be the more durable takeaway. You now own a template for reading earthquake news that most of the world does not have. The next time a cluster of moderate earthquakes makes a headline, and there will be one within weeks somewhere, you know the questions that separate signal from noise. Where do the events sit relative to the last great rupture on that boundary, and relative to its known gaps? Are the mechanisms interface or intraslab? Is the cluster decaying in place or migrating? What is the global background doing? Is this a loud week everywhere, or a quiet week with one lit window? And what is the base rate, the 19 in 20 gravity that most clusters obey? Those 5 questions are the entire working method of this video, and they are portable. They will serve you on the next Cascadia tremor story, the next Aleutian swarm headline, the next viral map of red dots that some account swears is the precursor to the end of the world. The dots are almost never the story. The geometry of the dots, against the ledger of what the boundary owes, that is sometimes the story. Learning to ask which is the closest thing to earthquake literacy our species currently possesses. Step back once more to the full width of the thing before we go. The Kuril-Kamchatka arc has been consuming the Pacific floor for tens of millions of years. It has erased a town and had the erasure erased. It has produced a top 5 earthquake under a government that hid the dead, and a top 6 earthquake under an open sky that saved nearly everyone. And the distance between those 2 outcomes, 73 years, 1 segment of trench, is the exact measure of what open information is worth when the ocean stands up. This weekend the arc spoke again, quietly, in 4s, on a silent planet, and what it outlined was the one piece of itself that has not yet had its turn in the modern era. The most probable future is that the outline fades, that the clusters decay, the tensors read intraslab, the gap goes back to its long accumulation, and this weekend files itself away as a footnote in a catalogue no one rereads. The rock does not owe us drama, but the rock does not owe us the most probable future either, and 80 millimeters a year compounds regardless of which future arrives. Somewhere under that cold strip of ocean, on a schedule no instrument yet built can read, the central Kurils are deciding what this weekend was. The question we leave open tonight, the one to check the catalogues for tomorrow and next week and every quiet week after, is the simplest one on the card. The centre of the map stayed silent through all of this. What happens on the day it doesn't?